All right. Hello, class. Hope you're having a good morning. I see three people are watching right now. I wanted to start off today just by going over an example. This should be a super easy lesson today, by the way. This is not going to take 20 minutes. It'll probably take 15 minutes. It's not that tough of a lesson, though. So I just wanted to do an example from yesterday. So we have a 12 battery connected to some resistors. And what I want to know is I want to figure out what is the current flowing out of the battery. Okay, so we're going to use the same rules that I taught you yesterday. To figure that out. Now I kind of intentionally drew this circuit a little bit weird. So one of the things you can see is that there's the 4 ohm resistor followed by the 2 ohm resistor. Okay. So that kind of looks like it's in series, but it's actually not in series. Okay. And the reason that it's not in series is because it's one resistor then another, but then there's this wire that comes out in between them and goes through that 7 ohm resistor. So those two are not in series. Okay. Another thing I wanted to point out is that this 2 ohm resistor kind of looks like it's in parallel with the 7 ohm resistor. They're both side by side, if you will, and but that's not the case. They're not in parallel. The reason that it's not parallel is because you can see the wire branches. It goes through each resistor, and then it actually this one, it goes through another resistor, and only then do the wires come back together. So that actually is not a parallel connection. Okay. And then there's a third thing in this circuit that is a little bit weird, which is if you look at this 1 ohm resistor, it has a wire that just goes around it. So what do we do in that case? You could think about this as a wire. You could think about it as more or less being a 0 ohm resistor. Okay, so this is like a 0 ohm resistor is in parallel with 1 ohm. Okay. So let's go ahead and figure that out. Let's use the formula for R sub P. So we have 1 over R sub P equals 1 over the first resistor, which is 1, plus 1 over the second resistor, which is 0. All right. Now, 1 over 0 is infinity. In physics, it's infinity. And in math, it's not defined. But in physics, it's infinity. So basically, we have 1 plus infinity, which is equal to infinity. And so 1 over R sub P equals infinity. And that means that R sub P equals 0. So when you have a wire that goes around a resistor, that's called a short circuit. It's like a shortcut. Okay? And so if you were an electron and you were going through this circuit, why would you go through a path that offers resistance when you could go through a path that offers no resistance? So basically, all the current is going to decide to go this way through the branch with no resistance. Okay? So if you have a wire that just shortcuts something, it basically nullifies that part of the circuit that got shortcutted. Okay? So that one we can just ignore the 1 ohm resistor. We can see that the 2 ohm and the 3 ohm are in series. So R sub S equals 2 plus 3 equals 5 ohms. So I'm going to redraw the circuit making those changes. And one of the things you can see is that I've combined the 2 ohm and the 3 ohm into 5 ohms. And the second thing is that I've just not even drawing the 1 ohm resistor anymore because it was short circuited by this wire. Okay. So now that we've combined these 2 resistors, we can see that the combination is in parallel with 7 ohms. So we have 1 over 5 plus 1 over 7 equals 1 over RP. So getting out my calculator. You guys probably can't read the screen. 1 over 5 plus 1 over 7 equals 0.34. And then I have to invert that. So answer to the -1 power, 2.9 ohms. All right, so redrawing the circuit again. We have 12-volt battery. We have a 4 ohm resistor. We have a 2.9 ohm resistor. Like that. These 2 are both clearly in series. And so we have R sub S equals 4 plus 2.9 equals 6.9 ohms. So that means that the total resistance is 6.9 ohms. Now once you have it down to 1 resistor in the battery, that's when you apply Ohm's law. So you say V equals IR. 12 equals I times 6.9. And then you divide both sides by 6.9. 12 divided by 6.9 is a current of 1.7 amps. So that's our answer. Okay? Lift this up so we can see the whole paper a little bit better. All right. So I'm going to flip over the page. That was review. Now we're going to go on to a little bit of new content. So what I wanted to talk about today was, first of all, what's called an ammeter. Okay, and the symbol for an ammeter is simply a circle with an A. Okay, and it is a device that measures. So ammeters always have to go in series with the thing that you want to know about. Okay, so going back to here, if I take an ammeter and I put it in series with the battery, that's going to tell me what the current flowing through the battery is. So if I put an ammeter right there in series, doesn't matter if it's in front or behind, as long as it's in series, it's going to give us the current. So this ammeter would read 1.7 amps. But one thing that's important to realize in circuits, and I think I mentioned this yesterday, that when you have a complicated circuit like this, that 1.7 amps is going to hit this junction, and it's going to actually split. Some of the current might go this way, some of the current might go this way. So everything in a circuit is going to get a different amount of current. The battery is the source of current. Okay, the battery is the source of the current, but so, you know, if I add up this current and that current, it's going to add up to 1.7 amps. but everything is going to have a different current in general. So what if I wanted to know what is the current through the 7 ohm resistor? I would put an ammeter in series with the 7 ohm resistor, like that. Okay, so that's how an ammeter works. You put it in series. Another thing I wanted to say just really quick is you always say the current through a device. Okay, so I can say the current through the battery or the current through the 7 ohm resistor. Okay, there's another device. It is called a voltmeter. Okay, and a voltmeter is denoted by a circuit symbol with a V in a circle, and it is a device that measures voltage. Okay, so to use a voltmeter, you must place the voltmeter in parallel with the device that you're interested in. Okay, so flipping over to this page here, what if I wanted to know, and just like current, every device is going, every part of this circuit is going to get a different voltage. Okay, the battery is the source of the voltage, but it's kind of just like the current from the battery is shared amongst all the things. The voltage is also shared amongst all the things, and we'll, as we go on and learn more about circuits, we will learn more about that. But if I wanted to know how much voltage is that 4 ohm resistor getting, I would place the voltmeter in parallel with it, like that. That would tell me the voltage across the 4 ohm resistor. What if I wanted to know what is the voltage across the 7 ohm resistor? I would place a voltmeter in parallel with it, like that. Okay, so that's how you use a voltmeter, and you always are going to say the voltage across. I think I'm back. Sorry about that. Thank you for commenting that I went away. That's helpful. There's a little icon that I can see when the upload rate goes. So I think I was talking for about a minute with no audience, and I just didn't realize it. But I can always fix it. All I have to do is just, reload it, basically. So we always say the voltage across the device. So it's the voltage across the 7 ohm resistor or something like that. Okay? So what I was saying is that electrical power is going to be the next thing that we talk about. Electrical power is denoted by P, just like other types of power. And so if we look at our original circuit here, this 12-volt battery is outputting power. So it's giving energy to the circuit, and the circuit is consuming that energy. So, and so what is done with that energy? Well, if it's just a resistor, resistors take that energy and they turn it into heat. Okay? But remember, this resistor could represent something that's not actually just a plain old resistor. It could represent a light bulb, in which case that energy is light, turning into light waves. It could represent a motor, where that energy is being used to spin something. So this resistor, it could represent a number of things, but it's using that energy. So let me give you a formula for electrical power. It's P equals current times voltage. P equals I times V. So that's our sort of new equation for today. And it is, if I flip the page over, we could calculate what is the power output of the battery. The power equals I times V. Well, the battery has a voltage of 12 volts, and it has a current of 1.7 amps. All right, so if I work that out, 12 times 1.7 equals 20.4 watts. So this battery is outputting 20.4 watts of power. Okay. We could also do I times V for all of the other devices in the circuit. So for this resistor, that resistor, that resistor, that resistor, that resistor. Now that the battery is outputting power, everything else is consuming the power. So if we were to add up all of these powers that all of these devices are consuming, guess what it would equal? It would equal 20.4 watts. And that's a reflection of the conservation of energy. So the energy that the battery puts out is the energy that the circuit is using. None of the energy disappears. Okay? We can take this equation and we can combine it with Ohm's law. So if I use Ohm's law, well, V equals I times R. And then I plug that in for V, I get I times R, which is I squared R. So this equation is an equation for the power dissipated by a resistor. I could also write I equals V over R, and I could substitute in for I, so I have V over R times V, and then I get power equals V squared over R. It's a little bit funny because that's also the equation for centripetal acceleration, but remember, for centripetal acceleration, V squared over R was speed squared over turning radius. This is volts squared divided by resistance. These two equations only apply for resistors. You couldn't use these equations, for example, on a battery, because for a battery, the resistance isn't defined. So this is kind of the master equation, and it always works, but if you have a resistor, these two work as well. I'm gonna, I think, stop there. Tomorrow I might talk a little bit about why we have high voltage power lines, because it has to do with this equation. I hope everyone's doing well, and I will talk to you tomorrow. Bye.